This is a quick little video showing you how to create a standard curve in Excel and then use that standard curve to get a linear best fit line, get the equation from that, and then use that to find your unknown concentration. So I have taken data from the paranitrophenol from your lab and put them into Excel. Here I have one column for concentration, one column for absorbance. You could also do it in rows. It would work essentially the same way. Older versions of Excel, if I highlighted all of these, would automatically put these as axis titles. I haven't had good luck with the newer versions of Excel doing that, so we don't really need it. We'll leave it and we'll see what happens. So I'm using Excel 2016. If you're using an older version, it'll look very, very similar. It's not exactly the same, but it's very similar. So I'm going to highlight all my data. I'm going to go insert, and I want a scatter plot. We do not want a line chart or a line graph. Scatter plot is for independent data points, which is what we have. Line chart is more for changes with time. So we're going to choose scatter plot, and we're going to choose the one without any connecting lines. And so we've seen that it's kind of randomly chose the absorbance and put that as the graph title. We don't need a graph title at all, so I'm just going to delete that. If you do need axis titles, and so you can go add chart element, axis titles. Here you would put your units, include the units in your axis titles. So we're going to add a trend line. So what I'm going to do is I'm going to right click on a data point. Go add trend line. I want linear, and if I scroll down, I can choose to display the equation and display the R squared value. You want both of them. And so those are there now. I'm going to close that, just move this so we can see it a little bit better. So the R squared value tells you how well your linear line matches your data. Now we can visually see it does not match very well. R squared of 0.81 is not very good. Generally we want this up in the 0.98, 0.99 range. Above that, here we have our equation for our best fit line. So if we look at our graph, we don't have the axes labeled yet, but the Y is the absorbance and the X is the concentration. And so the X here is the concentration, the Y is absorbance. And so idea is if you take any X value here, plug it in for X, the Y you get will be the point on the line. For your unknown though, we're going to work backwards. For your unknown that you know the absorbance is 0.268. That's 0.268. And so you would just get our calculator and plug 0.268 in for Y and solve for X. Whatever X comes back is going to be whatever your unknown concentration was. So 0.268 is going to fall somewhere in this area here. So you then calculate the X value, and that would be your unknown. Now, if we look at this, this obviously doesn't match. A standard curve from this type should be linear, and this is clearly plateauing. So something I want to show you is if we come back and we delete that, it looks a whole lot better. This is what it looks like to me, is either this one is a little too high, or perhaps if we do that, it looks really, really good. And so what's happening is your graph's plateauing. When you get to the higher concentrations, you're leaving the linear range of the detector. You do not want to include those points in your standard curve. My suggestion would be to use simply these 3 data points and put in your lab report that you got rid of the other 2 because they were outside the linear range of the detector. Now our R squared is 0.9923. That's perfect, great. So take your unknown absorbance, plug it in for Y, solve for X, and you have your unknown concentration.